Hey everyone! While sitting in my car here, I kind of figured I'd continue our quest to revisit the skills needed for success on our unit exam or our unit in kinetics and equilibrium. Let's see how much we could accomplish while the daughter is at cheerleading. Alright, question number 9. Given the potential energy diagram representing a reversible reaction. Reversible reaction. That implies that the reactants, if they reach enough activation energy and have the correct orientation of the collisions, effective collisions, it will produce a product. But conversely, what could also happen is the products, if they acquire enough energy, they will reverse. And it will tend to, these reactions will tend to reach a state of equilibrium if they do not go to completion. Alright, here's the question. The activation energy for the reverse reaction is represented by, well, here's the amount of energy for the products. And for the products to reverse back to the reactants, it must increase its energy this much. And which line represents that? Well, there is no actual one line. So it would have to be the combination of line C plus line B. What do we got here? We said C plus B. It says B plus C. Same deal. Alright, number 10 also shows you a potential energy diagram. Question is, given the potential energy diagram, an equation representing the reaction between substance A and substance D. So substance A and substance D are carrying this certain amount of potential energy. If it reaches its activation energy, it will become a product that is designated as G, and here's the energy for G. Question reads, according to table I, substance G could be. Well, let's inspect. Substance G has more energy than substance A plus D. So, if you compare the amount of energy in the reactants versus the product, well, it gained energy. And it gained energy in this fashion. It gained that much energy. So substance A and D was at this line. It climbed up to G. It increased in energy. And substances that absorb energy are known as endothermic. So we're going to look at table I and try to discover which substance is endothermic. Here is table I for you. And there's a hint down here. It says a minus sign. Where's my pointer there? A minus sign indicates an exothermic reaction. So we're not looking for a minus sign. We are looking for a plus sign when it comes to change in energy. Delta H. And which one of these? Well, we have, how about HI? HI, where are you on this? Here is HI, and that's a plus. Plus. What did it say again? It said a minus sign. That's down here. It said a minus sign indicates an exothermic reaction. So again, we were looking for the positive sign. And we found it. Now, it does appear though that we found it, but let's confirm by looking at the other choices. Where is our H2O, our water, production of water? Many of these produce water. Here you go. Here you go. A few different productions of water. Both of these are both negative, so that's exothermic. How about carbon dioxide? Carbon dioxide is here. Again, a negative sign. How about C2H6? C2H6, again another negative sign. So the choice that must be true, let me change to a pen, change the color, blue this time, it must be choice 1. It is the only one that is showing a positive delta H. Number 11. Given the diagram representing a closed system at constant temperature. Well, inspecting here, we do have a flask, an Erlenmeyer flask. There is a rubber stopper in there, and we have H2O gas in this portion, and H2O as a liquid. Okay, so which statement describes this system at equilibrium? Number one, will the mass of the liquid water equal the mass of the gaseous water, the vapor? Well, in looking at this picture, it kind of looks like there might be equal volumes, but let's hypothetically raise the volume to here. And if this was all water, well, then it would be very, very obvious that the mass of the liquid would not equal the mass of the gas. So choice 1 could not be true. All right, so let's get rid of that. Now let's examine number 2. Number 2 says that the volume of the water equals the volume, the liquid water equals the volume of the gaseous water. Again, if we were to raise the volume for demonstration purposes, we would notice that that does not have to be true. All right, now how about the number of moles? The number of moles of the liquid water equaling the number of moles of the gaseous water. Well, again, if we were to make it an extreme, it would be obvious that the moles of gas would be less than the moles of the liquid, so that can't be either. But what is true? When it is at equilibrium, the rate of evaporation from the liquid water to the gas will equal the rate of condensation from the gas to the liquid. So it would kind of look like this if we made it an equation. And, well, let me put it down here. I just ran out of space. So this suggests that the rate of the forward reaction going from a gas to a liquid would be equal to the rate of the liquid becoming the gas. Choice 4. All right. Number 12. Some solid potassium nitrate remains at the bottom of a stoppered flask, closed system, containing a saturated potassium nitrate solution at 22 degrees Celsius. Now remember, this is potassium nitrate. Do not let it throw you that it moved to the next line. But it says aqueous. That implies that the potassium nitrate has water with it, and it has dissolved. So we truly do have a solution. The potassium nitrate is the solute, while aqueous water is the solvent. Now, which statement explains why the contents of the flask are at equilibrium? So let's take a look at this picture here. And I drew this to suggest to you that we have a stoppered flask with water, and these yellow dots here are the potassium nitrate. Some are dissolved while some are now on the bottom, and the only way that they're going to land on the bottom is if the solution just above it is already saturated. So what is going to happen? Well, every single time one of these particles of solute crystallize and drop down to the bottom, well, then there's space for another one to dissolve and then become part of the solution. So, which one of these demonstrates that idea? Pause for a moment, read them, and I'll disclose. All right, I truly hope you did pause, and here's the answer. It is the rate of dissolving is equal to the rate of crystallization. Now, if that term rate is throwing you, the rate really implies the speed in which it's happening. Number 13, given the phase equilibrium in a closed container. Here we have gaseous water, so it's a vapor, in equilibrium with liquid water. And it is a closed container, so the system is closed. Question is compared to the rate of gas formation, so that's going to the left, the reverse reaction. The rate of liquid formation, the forward reaction, is, well, if it's in equilibrium, it must be the same. Now I've got a follow-up question down here. At what temperature does this happen? Now to answer that, we would need to address one of these phase change diagrams that we've done in the past. And what I'm going to show here is down here we have our solid, here we have our liquid, and here we have our gas. So what what portion of this are we looking at when we are talking about water going from gas to liquid, or even from liquid to gas? So gas and liquid, we are right here. And if this is water at standard temperature, this location right here, that would be 100 degrees Celsius. So at what temperature would this be occurring? Well, 100 degrees Celsius. Now this is a good time to review what could happen, or how is equilibrium reached between phases in a closed system. So let's look at this thinking map. The statement says if the solution is saturated, ignore that period there. If the solution is saturated and the system is closed, then equilibrium can exist between dissolved and precipitated solute particles. So the precipitated solute particles are the crystals that are on the bottom. Now why does this happen? Because if the solution were unsaturated, there would be no precipitate. So it's unsaturated means anything else you add will still dissolve. And because as one particle falls out of solution, precipitate, crystallize, another one must dissolve. This is a good one to pause and commit to memory. Okay, 14. Ammonia is produced commercially by the Haber reaction. This is what it looks like. They have nitrogen gas as N2 combining with 3 moles of H2 gas. It's a reversible reaction, producing 2 moles of ammonia as a gas and giving off heat, an exothermic reaction. Well, if their goal is to make ammonia, they want to force the reaction to go to the right. So how do we do that? So the formation of ammonia is favored by, again, we want it to go to the right. Well, something we have to identify. We have gases here, so we have to note that we have 1 mole of N2 gas, 3 moles of hydrogen gas, and that's in equilibrium with 2 moles of ammonia as a gas. So in total on the left, we have 4 moles, and on the right, we have 2 moles. Well, if we increase the pressure, what that is going to do is that will actually squeeze the gas into a smaller area. But which side gets affected more? And the one that gets affected more is the 4 moles gets affected more so than the 2 moles. So in essence, the left side, the reactant side, will behave as though it became more concentrated than the product side, and that will force it to the right. And which one is that? Well, choice number 1. All right, 15. Given the reaction at equilibrium, we have 2 moles of A, whatever that is, as a gas, combining with 3 moles of B as a gas is in equilibrium with 1 mole of A2B3 gas and heat. Which change will not affect the equilibrium? Not change it. So which will not change the equilibrium concentrations of either of the reactants or the product. Now, if we were to do what 1 says, and that's add more Ag, that's a reactant, it's going to force it to the right because now we have more opportunities for the reactants to collide. If they collide more, they make more products. If we add more catalyst, it just makes it go faster. So does that affect concentration? I'm thinking no. So 2 looks good, but what do 3 and 4 do? If we increase the temperature, well, temperature is on the product side. So temp, that will force it to the left because Le Chatelier said that when you add a stress, the reaction will move away from it. And 4 says increase pressure. Now we have 2 moles of this gas and 2 moles of this gas. I'm sorry, 3. That's 5 moles on the left in equilibrium with 1 mole on the right. If we did increase pressure, that too would push it to the right. So the only one that does not push the reaction in one direction is 2. It only goes faster. It doesn't change the concentrations.